So on Tuesday, we finished up talking about exponential functions and some applications of them, compound interest, growth and decay, that kind of thing. And so now we're kind of getting into this part of college algebra. We're sort of in the last month of the course where we're going to look more at some geometry, some analytic geometry, and then we kind of cap things off in chapter 9 talking about sequences. So the sort of the big functional families are done, okay? And now we're just sort of picking up parts kind of here and there. So what we're going to be talking about for the next the next week or so are what's called the conic sections. And literally a conic section is you take a cone and you slice it in different ways, and that's going to produce different curves. So if you take a cone and you slice it straight across, you're going to trace out a circle. If you angle it a little bit, you're going to trace out what's called an ellipse. If you slice it a little more, you're going to get a parabola. And if you slice it a little more, you're going to get what's called a hyperbola. Now, the parabolas we're going to talk about are the same parabolas we saw back in chapter 1, the same parabolas you saw back in algebra 2. But these other things may be new. Now, it turns out that algebraically, the way we describe each of these conic sections is a quadratic equation, not necessarily just in one variable. So it might be in more than one variable. So that's geometrically how we describe the conic sections. We can get at them using analytic geometry by using the notion of distance. So distance is another way we can describe each of these conic sections. And so let's go back and review how distance works in the plane. So suppose we've got 2 points, P and Q, and we're trying to figure out the distance between P and Q. Now, to be more specific for us, distance is going to be measured as the length of the line segment that connects P and Q. If you have 2 different points, they determine one line between them, and we're looking for the length of that line segment. So typically what we do is we exploit the fact that we have a right angle geometry available to us here. And so we can sketch in a little right triangle, and D then becomes the hypotenuse of this right triangle. So if I label this side A and this side B, then I can use the old Pythagorean theorem, A squared plus B squared is D squared. Now to figure out what A is, notice I'm just moving here in the X direction. It's only the X values that are changing. And so I can get the length of that segment by taking x1 minus x naught. And similarly, for B, I'm only moving in the y direction, so I can figure out how much I've changed in y by taking y1 minus y naught. And that's my formula for distance. So I can turn it around and solve for distance by extracting the square root, and that gives us the distance formula. Okay, so this really comes from the Pythagorean theorem. All right. Now another way I like to think about the distance formula that's a little bit easier to remember is that you think of that x, that's your change in x, so delta x squared, and that's your change in y, delta y squared. That's how I like to think of the distance formula. So let's do an example. Find and simplify the distance between the following sets of points. So distance is the square root of the change in x squared plus the change in y squared. And let's figure out the change in x. I take the difference of the x values, so I would take 1 minus a negative 2. which would really be a 1 plus 2, which is a 3. The delta y would be negative 3 minus 3. Once again, be mindful of the signs there. That would be a negative 6. And so this would be the square root of 3 squared plus negative 6 squared, which would be the square root of 9 plus 36, square root of 45. Now we can simplify that square root. As we've simplified square roots all along here, we look for perfect square factors, so there's a factor of 9 in there. Remember, square roots work well with multiplication. So my d is 3 root 5. And since they're asking for the distance, oftentimes we'll say 3 square root of 5 units. They didn't tell us if this was, meters, inches, centimeters, light years, whatever. So the distance is 3 times the square root of 5 units. Any questions on how to plug stuff into the distance formula? Where it comes from? Now I'll leave number 2 for you to do. Number 2 is just remembering how fractions work. So really number 2 is more about practicing fractions than the distance formula. Now what typically comes along with the distance formula is the midpoint formula. So what's the midpoint? Well, midpoint, think of that as middle point. And it's demonstrated here. This is the point that's halfway between P and Q. And so basically the idea is we're going to go halfway over and halfway up. All right. So to calculate that, we take the average of the x's. So if you're hip to statistics, usually they put a bar over that for average. And then the average y. So you're going halfway over, halfway up. So for example here, if we want the midpoint of the line segment containing P and Q, so the midpoint, it's your average x, average y, average x. We add the x's together, divide by 2, so that's going to give us a negative 1/2. Average y. We add the y values together, and that's 0. And so our midpoint would be negative 1/2, 0. Okay? Now, we could check that this is the midpoint. For example, we could calculate the distance between P and the midpoint. And that should be half of the distance we got from P to Q earlier. So we should end up getting half of 3 root 5. And that should be the same as the distance between M and Q. 1/2, 3 root 5. Okay. Let's plot this on Desmos to see if it seems reasonable geometrically. So our points were negative 2, 3, 1, negative 3. You can even label that as P if we want. 1, negative 3. Label that as Q. And then what did we get for the midpoint? Negative 1/2, comma 0. Label that as M. So yeah, that seems pretty legit. Okay, M looks like it's nestled halfway between P and Q. Any questions on the midpoint? What it is? Does it make sense how you find it? If you understand where these formulas come from, they're not as mysterious. You tend not to need to memorize them. Okay. All right, so once again, these conic sections, geometrically, you can describe them this way, but each of them has a derivation involving distance. So let's take a look at circles. Circles are the easiest ones to get the equation from with the distance formulation, because essentially you're just rewriting the distance formula. So if you think about what the circle is, how do you draw a circle? Well, you start off with the center point. So we're going to call our center here h comma k, and a circle is defined to be all points that are a distance r away from the center. So if you imagine taking a thumbtack and a length of string, the thumbtack goes on one end of the string, you tie the string around a pencil, keep the pencil taut, and then move it around. Okay. In the old days, there was a thing called a compass. We used to use in math class as it was a compass, and we would make circles that way. But if I think about what has to be true, then if I fix a center, if I know what I want my center to be, and I know I want my radius to be, then how do I know if a point x, y is going to be on that circle? Well, what you would need is you would need the distance from hk to xy to be r. And so this is exactly the distance formula. So the distance formula is delta x squared plus delta y squared has to be r. And so what is delta x in this case? Well, the change in x would be the quantity x minus h, quantity squared, y minus k, quantity squared. And then to get rid of the square root and make the equation a little more friendly, we've got x minus h squared plus y minus k squared is r squared. And this is what we call the standard equation of a circle. So as I mentioned before, algebraically, all the conic sections are going to be graphs of quadratic equations. And in this particular case, not only is the x squared, but the y is also squared. Now, one thing you'll note is that if you graph a circle, the graph of a circle does not represent y as a function of x, because it violates the vertical line test. So when we graph these conic sections, most of the time, there is one case where you're going to get a function. Most of the time, we're going to be dealing with graphs of equations that aren't functions. So these are graphs of more generally, they're just relations between x and y. So let's take a look at an example here. Whoops, that's the take home. We'll talk about that later. So here's the standard equation of a circle. This is what we just derived here. And once again, don't make this any more magical than it is. It's just an application of the distance formula. So to write the equation of a circle in standard form, we're going to group the common variables together, put the constant on the other side, complete this square, and we're going to review this here in a minute, and then divide through by the coefficient of the squares. All right. So for each equation below, graph the equation in the xy plane, find the center and radius. Okay, so let's look at A here. So the only conic section we've learned so far is the circle. Okay, now as we progress through chapter 7, we will talk about how to tell the difference between the conic sections as we get into the different ones here. But pretty much you've got two quantities squared. So if I go back to my definition, or my standard equation rather, of circle, the center here is HK. So notice, if the quantity is x minus h, the center is at h. If the quantity is y minus k, the center is at k. So it's the opposite here. Now that might ring a bell thinking back to transformations. So just a little side note here. If you had a function y equals f of x, and you looked at y equals f of x minus h, if you had the x minus h inside the function, what did this do? We would add h to the x, which would move to the right. And likewise, if you had y equals f of x, and you had a y minus k instead of just y, then you could add that k to the other side, and this would be to add k to the y, which would move up. You follow? So what we're seeing is another instance of these transformations, but they're just kind of built into the formula. Okay, and we'll talk about that here in a minute when we talk about sort of the progenitor of all the circles. Okay, but just keep that in mind. So we've got the opposite thing going on again. So in this particular case, if I wanted to identify the center, then it's x plus 2 quantity squared. So I'm going to take the opposite of that. It'll be at negative 2. Y minus 1 squared, take the opposite of that, would be at 1. So the center is at negative 2, 1. And what's the radius? Well, the radius squared is 4. So r would be the square root of 4, which is 2. Remember, when we talk about radius, it's always positive. So we don't bother with, we don't talk about r being negative 2. So are there any questions on identifying the center and calculating the radius for this circle? So at this point, we want to graph center negative 2, 1, radius 2. So here's our x and y. The center is negative 2, 1. So negative 2, 1. And I put like a little x or a little star. Well, actually, I use x for center. And then the radius was 2. So that means that I'm going to go 2 units left and right, 2 units up and down, and then I'm going to connect the dots in what I hope will look like a circle. Okay, I always like to write the word circle next to it so people know I've tried to graph a circle. Now, of course, Desmos can handle this. So once again, you have access to Desmos to help check your answers here. And so let's see that works. X minus 2 squared plus y minus x plus 2 rather. Thank you. Squared. it is. And we can check that our center is spot on. We can plot -2, 1. Now once again, the center isn't part of the graph. The graph itself is just the curve, but you can see here 1, 2 units, 1, 2 units, 2 units, 2 units. So there you go. All right. Any questions on graphing a circle? Okay. Well, now let's take a look at this next example here. 3x squared minus 6x plus 3y squared minus 4y minus 4 is 0. All right. So, in order for us to easily identify and graph a circle, I'm trying to get it to look like this. X minus h quantity squared plus y minus k quantity squared equals r squared. This doesn't look a whole lot like this. However, if you took the time and multiplied these things out, you would have an x squared minus 2xh plus h squared, y squared minus 2ky plus k squared equals r squared. So you can see that if you multiplied stuff out, you would get x squareds, x's, y squareds, y's, and a bunch of constants. Okay. So what we have to try to do is we have to try to reverse engineer to go from perfect squares that aren't complete to perfect squares that are complete. And so we have to talk about completing the square. All right. That's how we're going to do this. The first step is we're going to throw the constant 4 to the other side and get rid of it. For now, we're gonna declutter the left-hand side. Okay. And then we're going to factor out the coefficient of x squared from the x terms. So in this case, I'm going to factor out a 3. And when you factor out a 3, remember, you're going to divide. So 3x squared divided by 3 is x squared. Negative 6 divided by 3 is negative 2x. And we're going to leave a space. We're going to leave a space because what we want to do is we want to turn this into a perfect square quantity. Now we're going to do the same thing here with the y's. It's going to be a little more complicated. We're going to factor out the 3 from 3y squared. Divide 3y squared over 3 gives you y squared. Divide 4y over 3 gives you a 4/3 y. And once again, we're going to leave a space. And then that's going to be equal to 4. And we're going to have some spaces on the other side as well. Okay? What I want to end up with when it's all said and done is I want to end up with an equation that looks like this. So I have to change the form. Okay? So this is how completing the square works. What I'm trying to do is figure out this quantity comes from 3 times what perfect square quantity. And here's the recipe. All right, as long as we've got this as a 1x squared, this is going to come from x, and then I just cut this in half. So if I take negative 2 divided by 2, it's going to be negative 1. Now, if I multiply out x minus 1 squared and FOIL it out, I'm going to get my x squared minus 2x plus a 1. So in other words, this quantity factors into this perfect square. Plus 3 times, and now I want to do the same thing for the y. Y, and what do? I take half of the coefficient of y and put that in here. So if I take half of 4/3, that's 2/3. And now if I multiply this out, I get y squared plus 2/3 y plus 2/3 y plus 2/3 square plus 4/9. So what I'm going to do here, I think, just to have better notes, is I'm going to just write this out in a little more detail here. So I'm going to leave some space. So I'm going to try to illustrate here. So I'm going to take half of this to get to minus 1. And then I'm going to square it to get to 1. Plus 3 times y. Let's see, like that. Just trying to make it a little clearer. Some people just look at the notes; they don't watch the movies. So then we would take this, take half of this, and then we would square it. To get the 4/9. Okay, so that's you. As long as you factor out the coefficient of the squared term, then that's the recipe. You take half of this and square it, half of this and square it. And once again, if you took the time and FOILed out x minus 1 quantity squared, you will get x squared minus 2x plus 1. If you took the time to FOIL out y plus 2/3 quantity squared, you'd get y squared plus 4/3 plus 4/9. So at some point in algebra 2 or whatever, you've seen completing the square, but if it's been a while, that's the step-by-step there. Now, this gets us the perfect square quantities we want, but in order to do that, we had to add stuff to the left-hand side of the equation. And you know that if we want to keep the same equation, whatever I add on one side, I have to adjust by adding on the other side. So this is where we have to pay attention. In order to get this perfect square quantity, I had to add a 1 inside this quantity. But what did I really add to this side? I added 1 inside the quantity, but that 1's going to be multiplied by 3. So I really added 3 to that side of the equation to get that perfect square. And likewise over here, I added 4/9 inside the quantity. What did I really add to that side? 3 times 4/9. So I guess I'll write this as a 3 times 1 and a 3 times a 4/9. Okay, so if I do the arithmetic here, I've got 4 plus 3 plus 4/3 which is 7 plus 4 thirds. If I get a common denominator, that's what, 25 thirds? There we go. So the long and short of it is, our original equation was transformed into this equation. Oop, 2/3. So there's our original equation, and here's our new equation. And so consider this part of your homework. Start here and work backwards. Right? Start here and work backwards, multiply things out and simplify to show you can get back to the original equation, just to convince yourself that this is all legit. So in other words, if I want to graph all the points x, y that make the first equation true, I can just graph the points that make the second equation true. Now thinking back to what we're trying to get to, we're trying to get to x minus h squared plus y minus k squared is r squared. You notice here that there's no coefficient on these quantities. Here we've got a 3, so we can get rid of that 3 by dividing both sides by 3. And remember, when you divide by 3, that's the same as multiplying by a third. So if I take a third times the first quantity, I'm going to get x minus 1 squared plus y plus 2/3 squared. If I multiply 25 thirds times a third, that's 25/9. And so now we can see we've got a circle centered where? Well, I take the opposite here from the x, so I'm going to get a positive 1. The opposite here from the y, I'm going to get a negative 2/3. And what's my radius? Well, the radius squared is 25/9. So the radius is going to be the square root of that. Remember, square roots work well with multiplication and division. So that's going to be 5/3. Okay. Any questions on the completing the square? There's a couple examples of it. We will be completing the square throughout next week as well. So every day we'll be completing squares. And then once you complete the square, you divide through by the coefficient. And there you go. All right, so we can check this out. See if we got it. We got it right here. Oops. You can go ahead and graph that equation. 3x squared minus 6x plus 3y squared plus 4y minus 4 equals 0. And 1 comma negative 2/3 is where we think the center is. Call that. Label that. Boom. Okay, so we'll call that C. There we go. And we think the radius is what? 5/3? Oops. So is the radius 5/3? Well, let's find out. Let's make the steps 1/3 units. So we can count. Starting here, we got 1, 2, 3, 4, 5. So that's 5/3 this way. 1, 2, 3, 4, 1, 2, 3, 4, 5/3 that way. Boom, there it is. Okay? So that's how we can check our answer on Desmos. We would graph it on the graph there. We could check it on Desmos doing that. Okay? All right. So what about this function? It says the graph f of x equals negative square root 4x minus x squared. So at first glance, it doesn't look like this has any business being in this section. Okay? But remember, when you graph a function, remember we graph the equation y equals f of x. So what we're trying to graph is y equals negative square root 4x minus x squared. And if we square both sides, to get rid of the square root, y squared equals, the square is going to get rid of that negative, and the square is going to get rid of the square root. And so by golly, if we add the x squared and subtract the 4x from both sides, look what we've got. We're in the running for a circle. I've got the sum of two squares. If I could complete the square on the x, I should be ready to go. So how does complete the square work? Well, the first thing would be to factor out the coefficient of x squared. In this case, we're lucky it's just a 1. So I'm going to leave space. I don't need to worry about completing the square on the y, because we don't have any terms that are just y to the first power. And now how does it go? I start with my x, and what happens? I'm going to take half of that negative 4 to get me a negative 2, and then I'm going to square it to get me 4. Oh. And if I add 4 to one side of the equation, I'll have to add 4 to the other side. So if I think about x minus 2 squared plus y squared is 4, well, that's going to be a circle. The center is going to be what? I take the opposite here. That'd be positive 2. And what's hanging out here with the y? It's y minus what? Well, if you want to be pedantic about it, you could say this is y minus 0 squared. So center would be 2, 0. The radius squared is 4. That means the radius is 2. So if I go to graph this circle, I'd start over here. The center's 2, 0. Radius is 2, so that's my center. So I go 2 units left and right, 2 units up and down. And I would be graphing the circle. All right? But I wasn't asked to graph the circle. I was asked to graph this function. Now, as I mentioned earlier, the graph of this circle is not the graph of a function. It fails the vertical line test. So we have to go back. Before we squared things, we had y is negative square root 4x minus x squared. So the y's on this graph are always the what? Negative values. So the graph that I want, the graph of the function, is going to be the lower half of this circle. So the graph y equals f of x is the lower semicircle. Make sense? And once again, we can check this on Desmos. Let's get to a clean screen here. So let's check x minus 2 squared plus y squared equals 4. Boom. So you can see that circle there centered at 2, 0. And now if I look at the f of x I wanted, it was the opposite of the square root of 4x minus x squared. And so you can see that what's happening is that the function graph is just a lower semicircle. All right. So one of the big ideas in mathematics is changing form. We've seen this all throughout. Okay, that's going to actually be one of your questions on your final. You know, there's a 25-point project you're working on, and then there'll be a 25-point questions that go with it, and one of them it talks about changing form. So going back and looking at specific instances where we changed form to help us with a problem, and here's an example of that. We took this function, we didn't know what it was, identified it as the lower half of this circle, and there it is. So now we know all about that graph. Okay, number 3, then we kind of turn everything around. So instead of here's an equation, graph it using the standard equation of a circle. Now I'm going to give you information. You got to come up with the equation. Okay. So in part A, I give you information, and you have to find the equation. In part B, I give you a graph, and you have to work backwards. All right. So let's see. Find the standard form of the circle satisfying the following characteristics. The points -1, 3 and 2, 4 are the endpoints of a diameter. So let's talk about what the diameter of a circle is. So I got 2 points here, -1, 3 and 2, 4. They're the endpoints of a diameter. So a diameter is a line segment across the circle that goes through the center. So that's the key. It's a chord that goes through the center. So since it's a diameter, the center, it's called the center for a reason, is going to be in the exact middle of this line segment. And we know what that's called. That's called the what? That's called the midpoint. So the center of the circle is going to be the midpoint of these 2 points. And how do I get the midpoint? I take the average x, so I add the x's together and divide by 2. And the average y, I take the y's, add them together, divide by 2. And I get a half, 7 halves. Okay, boom. I've got the center. Now what else do I need? I need the radius. Well, what's the radius? The radius is the distance from the center to any point on the circle. So one way I could get the radius is take either of these points and find the distance to the midpoint. Or another way I could do it is I could take the distance between the 2 points, which would be the length of the diameter, and chop that in half. Now, I like the second method because the second method, we're going back and using information that was given to us instead of information that we've derived. If for some reason we made a mistake in this calculation, I don't want to compound the mistake. So I'm going to go back to the initial amount here. So my radius, or my initial values, radius here is going to be half the distance from -1, 3 to 2, 4, So that's 1/2 the square root of, once again, that's delta x squared plus delta y squared. So 1/2 the square root of, delta x is 2 minus a -1 squared. Delta y is 4 minus 3 squared. So this would be 1/2 the square root of, 2 minus a -1 is a positive 3. 3 squared is 9. Plus 4 minus 3 is 1. 1 squared is 1. So I get 1/2 root 10. And so that's my radius. And so the equation of the circle is going to be x minus the x coordinate of the center, x minus 1/2 quantity squared, plus y minus the y coordinate, squared equals the radius squared. And while technically that's fine, we can go ahead and simplify this radius squared. The 1/2 squared would be a 1/4. The root 10 squared would be a 10, so that's going to work out to be 5/2. So our final answer here would be x minus 1/2 squared plus y minus 7/2 squared is 5/2. Okay. Any question on building the equation of the circle given this information about it? As always, we could check our answer using Desmos. So let's check it out. So let's look at the circle. We got x minus 1/2 squared plus y minus 7/2 squared, and that's equal to 5/2. And what were the points that were supposed to be on it? -1, 3. And 2, 4. And just for reference, let's put our center in there. 1/2, 7/2. That's our center. Boom. Okay. Seems legit. Seems legit. All right. All right, any questions on this example? All right, next example. We're trying to find the equation of the circle whose graph is given below. So we're told this is a circle, and we've got a couple of points here. This circle would be called tangent to the x and y axes. Tangent meaning the circle kind of comes up here and just touches the x-axis and the y-axis. So you might remember that word tangent. If you're going into calculus, you're going to hear the word tangent quite a bit, and it means the exact same thing as it means here. So how could we go about figuring this out? There's a couple different ways to do it. Remember, we need a center and a radius. All right. So looking at this example, one way to do it is say, okay, well, where would these two lines intersect? That would be your center. Well, it would be at -2, 2. Center's at -2, 2. And then what would the radius have to be? Well, how far am I moving from the center to the points? Radius is 2. So my equation would be x minus -2 quantity squared plus y minus 2 squared is equal to 2 squared, or x plus 2 quantity squared plus y minus 2 squared is 4. Make sense or not, folks? Okay. Now, let's talk about sort of the origin circle here. So let's talk about a very special circle called the unit circle. The unit circle is so important, we have a whole course dedicated to it. So if you go on to trigonometry, you're essentially studying the unit circle. What is the unit circle? We see the word unit in here. So in mathematics, unit means something having to do with 1. Here's what the unit circle is. It's the circle centered at the origin with radius 1. And so what would that look like algebraically? Centered at the origin, remember the origin is the point 0, 0. So it would look like x minus 0 squared plus y minus 0 squared is 1 squared, or x squared plus y squared is 1. So here's the unit circle. Boom. Now it turns out we can think of every circle as starting with the unit circle and applying transformations. So how does that work? So if I take x squared plus y squared equals 1, how do I get it to x minus h squared plus y minus k squared equals r squared? Well, first thing we'll do is we'll replace x with x minus h and y with y minus k. So as we mentioned before, this will shift right h units and up k units. Oh wait, let's not do, no, I want to do the other way around. I need to do it the other way around. We're not going to do the shift first. We need to do the stretch first. So we're going to replace x with x divided by r and y with y divided by r. So this is going to stretch the x and y by a factor of r. Okay, so remember when you divide inside the parentheses, you're really multiplying the points. And so this would get us to an x squared over r squared plus y squared over r squared equals 1. And now we can do the shift. Shift h units to the right. And k units up. And then we would just multiply both sides by r squared. Okay, so to kind of show you this kind of in action here, this is what's nice about Desmos, is you can type in these parameters, x minus h squared over r squared plus y minus k squared over r squared equals 1. And we're going to add sliders for all of these things. And we're going to start with h and k at 0. And r is 1. So here's our unit circle. Okay? Now by adjusting the r, we can scale it. So for example, when r equals 4, I'm going out left and right. Instead of going out 1 unit in each direction, I'm going out 4 units in each direction. Okay? And then I can move. If I want to move to the right 2 units, I'll put h over here at 2. If I want to move down, I'll put k down to like -3. You follow? But by adjusting the r, you can see that transformation. I'm stretching or shrinking both the x and y direction by the same amount. So that's the magnification factor. The h controls the left and right because that's in there with the x. The k controls the up and down because that's in there with the y. So you can think of all circles as being translates or transformations rather of the unit circle. Okay, let's take a look at your take-home assignment. Excuse me. You may need to review completing the square. So that's in the appendix if you need it. We talked about number 1 already. So once again, number 1, this goes back to really the example we did. If you go back and look at the example in section 6.1, we did an example like this. It's an application of exponentials, very similar to the one we did in class. It's the same scenario, we just have a slightly different function. And number 2, this is like what we did today. So number 2 here, so you've got to put the equation into standard form. So you've got to complete the square here to get this to work, right? You want to get it down to this step. And then from that, so that's your standard form. The center then, that's going to be the HK, and the radius is going to be your R. And once again, you can check this on Desmos. If you plug this into Desmos, and then plug your answer into Desmos, the graph should be identical. Plug your center into Desmos, and then, like we did, adjust the units so you can count the radius. Okay, so I really encourage you to do that. Desmos is a nice tool to help you check your answer. And then number 3, that's like another one we did today, where you graph this by showing the graph as part of a circle. So once again, the key here is to write y equals f of x. Once again, you can check your answer on Desmos. Okay? All right, well, I think that's all we were meant to do today. Let me double check. Because we've got the completing the square. Usually if we have a something we need to remind ourselves about from the old days. Uh-oh. Please don't crash on me. Yeah, I think this is all we were meant to do today. Yep. Distance in the plane and circles. So then next week we're going to talk about parabolas and ellipses. So we'll have a day for each of those. And then hyperbolas. And then systems of equations. So these topics all kind of flow together. Even though this is from section 8.7, you'll see this really kind of relies on what we do here. So we have a day for each of these conic section species. Then we have 3 sections to do in chapter 9. And so there we are. We're at the end already. Okay, so we're at the end already. So as always, folks, I appreciate you tuning in. I hope you get a chance to enjoy the milder temperatures this weekend. And if nothing else, we'll see you back here on Tuesday.